Okay. For this picture, there are two words in it. One is called IGP. One is called EGP. That is an internal gateway. External gateway. The internal gateway is used in the local area network. That is LAN. Remember the LAN of the local area network we talked about in the first class? Exterior gateway routing protocol used in wide area networks. That is WAN. Their application scenarios are different. So how to distinguish them? This LAN and WAN are too abstract. IGP is called Interior Gateway Routing Protocol. EGP is called Exterior Gateway Routing Protocol. How to distinguish between the inside and the outside? We talked about something before. AS. That is autonomous system. I said it before. Within an AS, run the same dynamic routing protocol. The strategy is relatively simple. Is a network built by a unified manager, called AS. So what we call external and internal refers to an autonomous system, external and internal. Like a door. The outside of the door and the inside of the door are called inside and outside. Inside and outside of this agreement refers to the autonomous system. Then the interior gateway protocol refers to the protocol running inside the AS is called the IGP protocol. Exterior gateway protocol refers to the protocol running between AS is called EGP protocol. Then the typical EGP protocol running between AS. The BGP protocol currently used in the WAN. You will learn in the NP course in the future. There are many interior gateway routing protocols running inside the AS. OSPF, ISIS, RIP, EIGRP, etc. If you don't know Cisco before, I can tell you about EIGRP. Early on it actually belonged to both the interior and exterior. That is, it can actually also be used between AS. But unfortunately, it launched and opened too late. Now all the ASs on the public network are running BGP. EIGRP as a whole was born late. That is, appearing late. We will learn the configuration of EIGRP later. You will find EIGRP also needs to configure the AS number. So if some students know BGP, you will feel very kind. Because only the public network, that is, the AS number is only required between ASs. So you come across a protocol. The AS autonomous system number needs to be specified. Means that it can run between autonomous systems. It is not a pure interior gateway routing protocol. For EIGRP. First, it was launched relatively late. Second, it opens relatively late. That is, it can run both in AS, can also run between AS, and want to compete with BGP. But unfortunately, when it's launched and it's open to the market as a whole, the market has long been occupied by BGP. So EIGRP is sorry. Many functions have been developed, but in the end it was not put into use. EIGRP itself has a very good protocol mechanism. Just make it easy for everyone to understand. Will be covered later in the advanced course. AS internally called IGP. Between AS is called EGP. This is the difference between their names. Including AS itself is also a concept in BGP. It's better to take it out. Some students may ask, does internal mean the kind that does not include operators? In order to facilitate your understanding, I will draw another picture. For example, this is operator A. This is carrier B. This is the company. There are many routers in the company. Of course, between operators is also a router. But I won't draw. I'll just draw it. This is the device we're talking about. Future. The company may have business interconnection with the operator. First of all, let's talk about where these things are running. The IGP protocol will run within the company. Whether it is IGP, OSPF, or EIGRP, running between these devices. If the company is relatively large, need to do some information docking with the operator. A company is an AS. Is a private AS. Also numbered. The operator is a public AS. It also has an AS number. BGP is now running between the two ASs. Although now, only BGP is used in EGP. Then between operator A and operator B. They run on the public network. It also runs the EGP protocol. So we can also know the difference between them. Of course, the IGP runs among them. Because operators are now using ISIS of IGP protocol. OSPF they are not used. This is the usage scenario of various routing protocols. I made a distinction for you. Then when you come into contact with ISIS in the future, it is necessary to learn to be biased towards the direction of the operator. You will only touch this. Cisco doesn't seem to talk about it. Sometimes I will take it out and say it simply. But don't say much about it. Because it is not part of the routing switch. In the enterprise network, you must first understand. Within an autonomous system, we all use IGP. Carrier A is also an autonomous system. Of course. Carrier A between various distributions. They are also different. The autonomous system also runs IGP. It is also EGP when docking. It's all the same. Okay. Next. What we're going to talk about is EIGRP. That is the first dynamic routing protocol we touched throughout the NA phase. Same. Let's talk about a distance vector routing protocol and a link state routing protocol. Let's first look at the content of EIGRP. I just introduced to you. It is also an IGP protocol. Interior Gateway Routing Protocol. Also used inside an AS. It was previously a Cisco proprietary protocol. But now it's publicized. Need money. So, we often still treat EIGRP as Cisco's proprietary protocol. Because very few people actually use it. Unless it's still a pure Cisco environment. Otherwise it's hard to see. And in EIGRP, it will have its own algorithm. This algorithm is called the diffusion correction algorithm. That is dual. Also known as diffuse update. Well, I just told you. Like SPF. It is the algorithm used by OSPF and ISIS. Dual is the algorithm used in EIGRP. We will also talk about the specific content of this algorithm today, including how to judge distance vector routing protocol and link state routing protocols. Depends on what it interacts with. Because EIGRP interacts with the routing table. So we call it a distance vector routing protocol. But it combines link state. Usually. It also has link state features. But it's essentially a distance vector protocol. Okay. We will learn it formally next. There is a sentence in it. I need to give you an explanation. Here you can see. It supports many network layer protocols. Apple Talk, IP, Novell, and NetWare etc. But in fact, now the most used network layer is the IP protocol. Some students will ask, can static routing be considered an IGP protocol? Okay. For static routing, it cannot be considered an agreement. A static route is just a single static route. Because it has no algorithm. It also does not need to specify a range. Static routing can also be used on the public network. Because it is not an algorithm. So it does not belong to the IGP agreement. Or the EGP agreement. Let's explain IP. The others are not commonly used now because we're not going to explain. For the IP protocol, the first thing you need to know is when we are talking about the third floor. I actually told everyone. The IP protocol we are using now is IP version 4. Internet Protocol version 4. We now also have an IPv6. You may be interested in IPv4 and IPv6. It's more about staying on the IP address. But the IP address is actually a field in the IP protocol. A source IP and destination IP is a field. Actually, what we're talking about, IPv4 and IPv6. The two large framework protocols. Then why is there only one IP written here? Is it because we still have to compare with OSPF? What OSPF learns in the NA and NP stages is version 2 of OSPF. So in fact OSPF also has version 3. So for the current IPv4 network environment, when running OSPF, in fact, version 2 is used. If the IP protocol migrates to version 6 in the future, let's run OSPF to use version 3 of OSPF. Because there are some mechanisms in version 2 and version 3 are different. And for different IP protocols, what it serves is also different. So, if the future really migrates from version 4 to version 6 era, we are now deploying IPv6 addresses on a large scale. This is the overall transition. If in the future, we hope to see single-stack IPv6 all over the world. Relatively speaking, it is still relatively long. Have to be decades. Single-stack means IPv4 is completely useless. IPv6 only. In fact, this is a very long process. But for the present process, if it really came to that age, IPv4 has really migrated to IPv6. When you go to use OSPF again, version 2 cannot be used. Can only use version 3. That is a transition issue between protocols that I highlight. Protocols like OSPF. It is impossible to make a smooth transition. You have to completely modify the current overall configuration. Because the version is different, the configuration is also different. It has no way of smooth transition. But why bring it up and talk about it? Because of EIGRP it's not the same. EIGRP is version agnostic. That is, whether it is the current version 4 or the future version 6. No matter which IP protocol you choose, EIGRP works as usual. It also does not need to modify the configuration. It is unversioned. So in the future if the transition, it can do a very smooth transition. Updates with little impact on configuration. It does not serve version 4 or version 6 alone. Here's the difference between them. Next, let's talk about its characteristics. A lot of this is nonsense. I pick some key ones. First let's talk about this advanced distance vector. It is an advanced distance vector routing protocol. Look here. It is a distance vector routing protocol. It's just more advanced. Where is the senior? I just said. For RIP. It's like someone gave it a cooked meal. It ate directly. It looks at the devices at both ends locally. Then send the data to others. But for EIGRP, are different. For these devices, it is also the interconnection of multiple devices. This is R1. This is R2. This is R3. After R1 calculates his own, directly give to R2. Then, for R2, it will take in R1. After that, it is not calculated locally before sending, but after taking it in. Take your own and send it directly to the other party. Then calculate it yourself. Every device is like this. So, its overall sending speed is much faster than RIP. Of course, from the point of view of what we just said about eating, it doesn't really make a difference, because it also passes the routing table. But it's coming soon. It will not be counted and sent after it is received. Instead, after receiving it, I even take my own and send it out together. Then run it locally. It's an algorithm question. The specific algorithm will focus on the NP stage. Algorithm is not as simple as I say now. In the NA stage we don't need to know much. Secondly, it has a feature. Fast convergence. EIGRP has a table called the topology table. If you have learned OSPF before, you probably know that OSPF also has a topology table. But it is not as strong as EIGRP. Topology table in EIGRP. It can put some backup paths inside. Pay attention to my words. You can put some backup paths. What are these paths used for? If there is a problem with the main line in the future. For example, data to destination. I will not draw the device between the two lines. Above is the main line. Here is the backup line. Once there is a problem with the main line, the alternate line will immediately appear in the routing table. Notice, is immediately present in the routing table. Then achieve a fast convergence. Let me tell you. How is this different from the static we just talked about? Some students may have doubts. Then the static interface was broken just now. Didn't the other one appear immediately? Do you all have such questions? Just now that also appeared immediately. But it is not the same as dynamic routing protocol. The one that appears immediately is due to your manual configuration. A separate backup path is allocated there. This is a static configuration. Please pay attention. This is the configuration. And for dynamic routing protocols, the backup line is calculated by itself. I guess it's a backup line. It is calculated. It's not one of your configurations. So for EIGRP, it can now calculate the data in the network. For example, there are multiple routes to the destination, and it can choose if this line meets the principle of entering the topology table. We can put it in the ellipse topology table. If the main line fails, I can immediately make this line appear in the routing table. And forward. It's a really nice mechanism for it. OSPF can't do it. Achieve a fast convergence. How can it be achieved? What kind of lines are eligible to enter the topology table? That's a question we're going to talk about today. Including here is another one called loop-free routing. I will tell you. Whether it's what we call EIGRP. OSPF is also good. ISIS is also good. They will all calculate the topology by themselves. That is, dynamic routing protocols are essentially loop-free. Because they need to understand the information in the network. You will learn topology drawing later. When the information in the network is drawn. These network devices. How to connect each device after receiving the information. They can be calculated by themselves. After the calculation, it can know whether there is a loop in the network. And has its own some anti-ring means. Based on different mechanisms. But we won't talk so deeply at this stage. So everyone understands that it is acyclic. That is, for each dynamic routing protocol, You don't even have to worry about loops. Unless you have some redundant configuration. For example, you configure a virtual connection for OSPF. This may create a loop. But we will not at this stage. That is, if you don't configure it normally. Do not do those configurations that make it cause a loop. It won't have a loop. We won't talk about the trigger update later. Because when I talk about appearances, we'll tell you about this. Let's look down. Here is an equivalent load balancer. And non-equivalent load balancing. In fact, the balance is not appropriate. In fact, it is more accurate to say that load sharing. Because it can't achieve true balance. The traffic will still be worse. But let's just say, do equivalent load and non-equivalent load. What does it mean? This has to be a separate picture. Okay. Let's take a look. For example, now here is a device. There is also a device here. There is also a device above. There is also a device below. This is R1. There is a route on the right. It is on the 1.1 network segment. For example, after I run EIGRP. So now R1 can learn this route from both above and below. Then according to the routing table addition principle. Under the same agreement. We start by comparing the routing metrics. Whoever has the smaller value will be added to the routing table. If the measure is the same. For example, above is 1000. Below is also 1000. Of course it's usually not that small. Wait a minute, we'll look at the specific parameters. Then they will all be added to the routing table. Since they are equivalent. We call this table addition equivalent load sharing. Then there is another situation. If the measure is different, we call it non-equivalent load sharing. But you may find it a bit strange. If the measure is different, isn't it possible to add the smaller metric value to the routing table? Shouldn't the ones with larger metric values be added to the routing table? But EIGRP is different. EIGRP can use some special methods. Let both appear in the routing table at the same time. If I change it to 10,000 above, the following is still 1000. These two items can be added at the same time. But the following one is better. The above one is worse. Unequal load sharing. I can have them appear in the routing table at the same time. How to do it we will see today. Of course. Today we will show you the contents of the topology table. Let's talk about this when the time comes. Just know that it has such a mechanism. Actually not very common. Let's go on. Flexible networking design. It is to update later. It is for network equipment. No restrictions. Not like RIP. Finally. Talk about this multicast and unicast. For multicast. First of all, EIGRP uses multicast for. Our overall data interaction uses multicast. Then for RIP. RIP version 1 uses broadcasting. Bad radio. I simply draw a picture to explain. For example. Now this device. Run RIP. For RIP. When the information is updated. Suppose there is a switch in the middle. A PC is connected here. It's okay. Two routers connected to one switch. There is also a PC connected to this switch. Then if RIP is delivered through a broadcast form. When the two of them are exchanging information. PC can also receive this data. That's the bad thing about broadcasting. It is not necessary to receive this data. Secondly. Now they are exchanging routing table. It acts as a PC. What if it's an attacker? The data of the device is broadcast to the PC in this way. It's for us. The privacy and security of the network is also not guaranteed. So broadcasting updates is not a very good approach. For unicast, you can't see it in EIGRP. You have to be inside OSPF to see it. You will learn the NP stage in the future. When learning OSPF, you will learn about a network called NBMA. Under this type of network, it communicates overall via unicast. But we can't reach it at this stage. Of course, OSPF still uses multicast more. Same as EIGRP. This is the communication between them. How to understand this multicast? In fact, I told you briefly before. Multicast is. These devices can be added to the group before communication. So how do we define multicast when we run EIGRP? Is that you have EIGRP running on the device. And after the declaration is completed, the group will be added automatically. This is called protocol-based grouping. It is added automatically. What's the benefit of this grouping? Is equivalent to. You can listen to an address of this multicast once. I will send some information in the future. Send to such a logical multicast address. As long as the device is added to this group, I can monitor the contents of this address. Then I can receive the data. This is what we call multicast. You will learn about the specific content of multicast in IE. Like WeChat group chat. You want to message someone right now. You have several ways. For example, private chat one by one. You can also choose. Pull these people into a group. Then talk to all of them. Then some students may ask, what is the difference between broadcasting and it? Give another example. For example, your company has about 100 people. You have a WeChat group. Suppose there are 20 people in your department. You have a better relationship. You have a separate group chat. This is your group. For broadcasting, it means you are within the scope of your company. You send a data that everyone can hear. But sometimes, you just want these 20 people to listen. You have a small channel. This is called multicast. If you want to send data to others alone in the future, sending one by one is called unicast. Look down. Support VLSM. We still have to draw a simple picture. Don't look at it just a few words. There are a lot of things involved. A PC. 2 routers. This router has a network segment here. Suppose this network segment is 172.16.1.0. 24-bit mask. Okay. It is clear. This is a Class B address. No matter what the bar 24 behind it is. It must be subnet. Otherwise, according to the rules, it starts with 172.16. Should be a 16-bit mask. This is a standard Class B address. And it is still a more specialized address. We talked about address classification before. You will find that it is subnet. If the routing protocol does not support VLSM. For example, this network segment is finally transmitted to this device. It learned, but not supported. Don't care what the data is. In the end, it will only learn and spread according to the main class. That is, the final data goes here. For this device, it passes 172.16.0.0. 16-bit mask. Because the main class of this address is a Class B address. Then the device will eventually propagate and learn according to the Class B address. Then if the device supports VLSM, it issued 24. Then what it learns is 1.0 bar 24. So if the device does not support VLSM, what it actually learned was wrong. Because it is obviously a 1.0 bar 24. It learned a 0.0 bar 16. This is definitely not right. So this is what we call VLSM. Okay. Let's finish the last point. Finally, there is a support for WANs and LANs. This is what I just told you. When EIGRP first came out, it supports the use of the wide area network. That is, support use on the public network. Why not now? Because it appeared relatively late. When it comes out and wants to open the market for free, the entire internet is deployed. And it charges. So gradually it will be forgotten by everyone. How much have you forgotten? Many people only think that EIGRP is a Cisco proprietary protocol. Just like OSPF. Many people don't even know. It used to be deployable on the public network. Actually, this agreement is really powerful. Now only used on IGP. But in a moment we will learn about its configuration. Everyone should know. It will have some corresponding AS number configuration. When we are learning EIGRP as a whole, there are 3 tables. Look. Neighbor table, topological table, and routing table. When we learn OSPF in the next class. Also 3 tables. Neighbor table, topology table, routing table. Both of them are the same in this case. The overall timing is not quite right. So whether it is technology or market, timing and opportunity really matter. Okay. Let's take a look at these tables. For dynamic routing protocols, its appearance will be more. Because you can only see static routes in the routing table. It has nothing else. Static routing does not have a static routing table. But dynamic routing will have a lot of appearances. Because it's complicated. So many tables will be generated. Let me tell you the contents of the table first. For example, there are now 2 devices. EIGRP is running between the 2 devices. Then they will exchange messages with each other. They interact to do hello packets. Is a greeting message. Then after the exchange of this message, the 2 of them will establish a neighbor. It's like you open the door and say hello to your neighbor. You 2 will be neighbors from now on. Once the 2 devices establish a neighbor, each will generate a neighbor table. The contents of the table. It's the picture I'm showing now. Let's take a quick look. First look at the first H here. 1 is 0. 1 is 1. This is the order in which neighbors are established. In computer language, the first digit is always 0. The second digit is 1. So it means that the following is the first established neighbor. The above is the second established neighbor. This is the order between them. This is just an identification. The following is more important. This one is called address. Please be careful. Whether it is the EIGRP we are talking about today, or OSPF in the next class, this representation is called the neighbor table. There is a very important word in the neighbor list, called I see the neighbors. That is, parameters seen by the device in the neighbor table. Not its own parameters, but the parameters of the neighbors. So this address, it is not the address of the interface of this device, but the neighbor's address. Everyone can see. This device is R1. Then according to the current overall configuration specification, it should be XXX1. But what you see here is the address of point 2. That is, here the device looks at the neighbors. It looks at the address of this interface of the neighbor. This is the address inside, instead of the address of the interface of the device. Due to more appearance, people often get confused when viewing. So I emphasize here, is the neighbor's address not the device's address. Include interfaces whose interfaces are also neighbors. Neither is the device's own interface. Go down and look at this uptime first. This is how long the neighbor lasts. That is, devices and neighbors greet each other. From the beginning to the present. The time they've been together. Don't look at the following parameters. This will be discussed at the NP stage. None of these 4 parameters will be mentioned. You will learn the protocol mechanism in the future. After learning the message, learn them again. Let's finally talk about this hold called duration. EIGRP is not only about establishing neighbors, but also to protect the neighbors. Then EIGRP sends a hello packet every 5 seconds. Then, if the device does not receive the other party's hello packet within 15 seconds, on behalf of the device thinks the neighbor is down now, the device will revoke the neighbor. That is, it thinks the neighbor is gone. It is removed from the appearance. Then this hold means every time the device receives a hello packet from its neighbor, it will refresh this to 0. Then start counting up. If you haven't received it in 15 seconds, it won't want this one. As long as the device is in the process of countdown. If it is received within 15 seconds after reading, becomes 0. Refresh. Becomes 0 again. Rebrush. It's like a timer. It's just timing. Count down from 0. Stop when the timer reaches 15. That's what I mean. I give a real example. You should go out to say hello every day. Suppose you say hello to your neighbor every 5 days. Then you find you opened the door and saw him after 5 days. You greet him. He ignores you. You say hello again. He still ignores you. 10 seconds passed. Say hello again. He still ignores you. 15 seconds passed. You think this person doesn't want to talk to you. You don't want him. You think this person doesn't reply to your message. Is he gone? The 11 here is. It's been 11 seconds now. The device has not received. Sometimes when we are doing experiments, this parameter is not particularly accurate. So it's enough for everyone to understand. Look down. This is a topology table. What does topology table mean? Let me tell you first. There is a routing table in the back here. This is very familiar to everyone. There is a D here. I'll explain what this D means in a moment. Let's go back and talk about this topology table. The topology table has an all links here. I see a classmate asked, are EIGRP adjacent routers neighbors? Yes. The device will only exchange packets with its current adjacent router. Actually, the same is true for OSPF. Must be a neighbor. Otherwise, there is no way to exchange messages. We'll wait while we make the announcement. The device needs to declare the directly connected network segment between it and its neighbors. So the device and it must be connected. Otherwise, they are not in the same network segment. There is no way they can be built like this. If they cross network segments, the two of them will not declare the same network segment at all, unless they are connected like this. Let's look at this topology table. Before this, I need to open up the experimental environment we did today. Otherwise, there may not be enough time for a while. Okay. There are several parameters in the topology table. For everyone to understand, we just look at this 4.4.4.4. Because wait a minute, we do experiments and we do it. In the topology table you will find, when data goes to a destination, there will be multiple next hops. And there are 2 parameters in the next hop. You will find that these 2 parameters are not the same. But they all appear in the routing table. So we're going to talk about something today. Let's look directly at this picture. This diagram is very simple. There is a loopback port on R4. The address is 4.4.4.4. That theoretically, there are two ways for R1 to go to 4.4.4.4. That is, the upper and lower roads. But please be careful. We're talking two ways to get to this address. But not necessarily these two paths will appear in the topology table. This is different from what everyone thinks. At the beginning of our study, we may feel that. How many ways to go to the destination? Put these roads as backups in the topology table. Not like this. Appearance in the topology table is conditional. It does not mean that there are several roads that can appear in the table, but both routes generate a topology. That's right. But not necessarily into the topology table. Whether it can enter the topology table or not, we can distinguish it according to its commands. First, type show IP EIGRP topology on your command line, called all links. If you enter a command like this, if you add all links to the command, then as long as there is a line from the originating node to the final node, as long as there is a physical connection, it will appear in that table. But if you enter the command without this all links, then there are only true topological lines will appear in the topology table. This is a real topology table. This is called the physical wiring list. That is, you can see all the lines. There may be many routes to the destination, but they do not necessarily all become the contents of the topology table. For some next hops that do not meet the conditions, won't put it in. Okay. Let's look at the routing table next. Here is a command. Show IP route EIGRP. Do you know what this means? When we check the routing table every day, it is show IP route. Now there is an extra EIGRP in the back. Just look at the routes learned from EIGRP. If there is an extra OSPF behind, just view the routes learned from OSPF. EIGRP starts with D. So here we have a question. There is a problem of managing distance in the back. When I talked about managing distance before, I told you administrative distance is actually divided into internal and external. EIGRP administrative distance inside is 90. External is 170. What does this external administrative distance mean? I give a simple example. For example, here are two devices. Both devices are running EIGRP. Then the internal administrative distance is 90. Here is a network segment. There is also a network segment here. Suppose this is the 1.0 network segment. The right device learned 1.0 on the left device. In its routing table, 1.0 the administrative distance of this routing entry is 90. But if one day there is a device here, the interface of this device and the interface of the left device are up by OSPF. Both of them are running OSPF. Agreement changed. Assuming this has a network segment of 2.0. Although here is OSPF. Here is EIGRP. But I hope the device on the right can learn the 2.0 network segment in OSPF. So how to learn it? They are not running a dynamic routing protocol. I just said different routing protocols are running between devices. They cannot directly exchange information. We have a method. Redistribution. I can redistribute. Then on this device, put the content in OSPF, introduced into the root of EIGRP. This is called redistribution, also known as routing import. Then now, it will be passed to this device of EIGRP. This device will learn the 2.0 network segment in OSPF. But for this device, it is also learned through EIGRP. But it is learned via EIGRP redistributed incoming routes. Then this administrative distance is 170. Finally, here is a summary. You may not be able to learn this at the NP stage. Might learn it in IE. Don't need to understand at this stage. And this value will not appear in the routing table. It is an implicit. As for what it is for, we can't get involved now. So you just need to understand the inside and outside. We are still talking about the interior. Now there is no redistribution involved. This is what is covered in advanced courses. Let's move on. Update multicast address. That is, when we use EIGRP, the multicast address it uses is 224.0.0.10. This needs to be remembered. By the time we learn about OSPF, that's 0.5 and 0.6. It uses 2. EIGRP uses 1. 224.0.0.10. And the protocol number is 88. EIGRP is encapsulated on top of IP packets. There is a protocol field in the IP packet. If it refers to 88, indicates that the upper layer uses the EIGRP protocol. If here is 89, indicates that the upper layer uses the OSPF protocol. You just need to know this. Don't ask you to remember it. Okay. Next we will learn the algorithm of EIGRP. The algorithm of EIGRP is called dual. The first is the acyclic path. This thing you will learn in the NP stage, because this involves how the algorithm draws the topology. We can't get in touch at this stage, because it is more difficult. What we have to learn is the alternate path. Fast convergence. This is the core of what we are now explaining. A loop-free backup path is, if the data has 2 lines to the destination, the above route is the best. The optimal one must be added to the table. There is no doubt about this. Then the ones that are not so good will not necessarily enter the topology table. Is to be considered. Wait a minute and we'll figure out how to calculate it. If there is a line, it is selected and added to the topology table. As long as this line is cut off in the future, this line can start forwarding immediately. This is where EIGRP is very powerful. OSPF is impossible. How to meet the conditions? This has to wait till the end, because its overall design is at the end. We just saw. There are 2 next hops in the topology table. Refers to this. The one above will be the main line. Into the routing table. Because in the routing table you can see it too. That for now. It also appears in the topology table. We can implement its addition table later. Let's talk about this later. Here's some of the algorithms we're talking about. Fast convergence is when the overall topology changes. A fast convergence can be achieved. This word is not easy to understand. Convergence is the synchronization of information as a whole, and optimize the current forwarding path. Realize normal forwarding. The forwarding speed of EIGRP is very fast, since it has the contents of the current topology table. So it can achieve a very fast convergence mechanism. But I tell you, if now there are 2 lines, this line is the main line. In routing table, this route is a suboptimal route, but it doesn't satisfy the condition. If it is not in the backup topology table, then it has no way to forward it immediately. It also requires a protocol mechanism. Do the calculation yourself. That is, it can be added to the list is conditional. But if entered into the table, it's switching in seconds. Let's look down. This algorithm actually draws a picture. I'm in this experiment. Restore this picture. Let's just wait and do it.